Welcome to today's webinar, Amazon EC2 Container Service Deep Dive. Our presenter is Pierre Steckmeyer. Pierre is an AWS Solutions Architect with a background in tech ops for the finance industry. He gets excited about technology shifts like containers, serverless architectures, 3D printing, blockchains, and more. Today with us, we also have Aaron Kao, Senior Product Marketing Manager for Microservices, and Andrew Thomas, Senior Product Manager for Amazon ECS. Aaron and Andrew will engage with you and answer your questions throughout today's presentation where Pierre presents. Pierre, welcome, and now pass the floor to you.
Thank you, Bowen. Hello, everyone. My name is Pierre Steckmeyer. I'm a solutions architect for AWS, as Bowen said, and I'm here to talk to you about EC2 Container Service. And more specifically, I would like to go beyond the basics and into more advanced uses. Here are the topics for the day. A quick recap on the reasons for using containers in Amazon ECS. And then we will dive deeper on clusters, tasks, and services. And finally, we will discuss a few solutions built on Amazon ECS. In the last few years, containers have gained a lot of attention. Let us understand what makes them so popular. In a way, containers are similar to hardware virtualization, like EC2 instances. However, instead of partitioning a machine, containers isolate the processes running on a single operating system. This is a useful concept that lets you use the operating system kernel to create multiple isolated user space processes that can have constraints applied to them, like CPU and memory. The Docker command line interface makes using containers easy with commands like docker run, docker push, etc. Docker images make it easy to define what runs in a container, and they constitute versions of the entire application. These concepts enable automation. You can define your application, build and share the image, and deploy that image. Now, you may be thinking, this sounds interesting, but why would I want to use containers? Well, there are 4 key benefits to using containers. The first is that containers are portable. The image is consistent and immutable. No matter where you run it or when you start it, it'll be the same. The image works the same way on the developer's desktop, on a QA server, and in production in the cloud at scale. And a container is usually small, in the range of 10 megabytes, tens of megabytes for an image. It's very shareable. Containers are flexible. You can create clean, reproducible, and modular environments. Containers make it easy to decompose an application into smaller chunks, like microservices, reducing complexity and letting teams move faster while still running the processes on the same host. There is no library conflicts. Simply stating that Docker images start fast sells the technology short, as speed is apparent in both performance characteristics and in the application lifecycle and deployment benefits. So yes, containers start quickly because the operating system is already running and you're addressing the kernel directly. But every container can be a single-threaded development stream with less interdependencies. And then finally, containers are efficient. You can allocate exactly the resources that you want. You can specify CPU, memory, the disk, network. Since it shares the same operating system kernel and libraries, containers use less resources than running the same process on different virtual machines. The Docker command line interface is great. If you want to run a container on your laptop, for example, you can just type docker run my image. But it's challenging to scale to hundreds of containers. Now you're suddenly managing a cluster, and cluster management is hard. You need a way to intelligently place your containers on the instances that have the resources, and that means you need to know the state of everything in your system. For example, what instances have available resources like memory and ports? How do I know if a container dies? How do I hook into other resources like a load balancer? Can I extend whatever system that I use, such as a continuous delivery deployment pipeline or a third-party scheduler? Do I need to operate another piece of software? Well, these are the questions and the challenges that our customers had, and which led us to build Amazon ECS. Amazon EC2 Container Service is a highly scalable, high-performance container management service that supports Docker containers and allows you to easily run applications on a managed cluster of Amazon EC2 instances. Now, running modern distributed applications on a cluster requires two key components. One, a reliable state manager, and two, flexible scheduling. Amazon ECS handles the complexity of cluster and container management, so you do not have to install and operate your own cluster management infrastructure. State management is exposed through a simple set of APIs that give details about all instances in your cluster, all containers running on those instances. Amazon ECS APIs respond quickly, whether you have a cluster with one instance and a few containers, or a dynamic cluster with hundreds of instances and thousands of containers. A scheduler understands the need of the system, the work that needs to be done in order to start a container that needs, let's say, 200 megabytes of memory and TCP port 80. And it looks to efficiently satisfy these needs and then submits a request to the cluster state manager. ECS provides optimistic concurrency control so that other schedulers may be operating at the same time. Cluster management confirms the resources that are available and commits them to the scheduler. The scheduler can then listen for events from the cluster manager and take action, for example, to keep the availability of your applications. ECS has two schedulers to find instance placement based on resource needs, isolation policies, availability requirements. This combination of cluster state management and flexible scheduling offers shared state optimistic concurrency. Amazon ECS is built to work with the AWS services that you value. You can set up each cluster in its own Amazon Virtual Private Cloud and use security groups to control network access to your EC2 instances. You can store persistent information using Amazon Elastic Block Store, EBS, and you can route traffic to containers using Elastic Load Balancing. AWS CloudTrail integration captures every API access for security analysis, for resource change tracking, and compliance auditing. ECS can easily be integrated or extended through a simple set of APIs. This provides complete visibility and control into your AWS resources. You can use your own container scheduler or connect ECS into existing software delivery process, such as continuous integration, continuous deployment. Now, the container agent is open source, and it is available on GitHub, so feel free to discover it, provide feedback, and pull requests. Let us now go briefly through some terminology. A cluster is a collection of resources, primarily instances and containers. Container instances are EC2 instances with the Docker daemon and the ECS agent installed. You can have container instances in multiple availability zones that belong to the same cluster. It is just a big bucket of resources, of CPU, of memory, etc. A cluster is dynamically scalable. It is possible to have a one instance cluster or a 1,000 instance cluster. And clusters can be used to segment for particular purposes. For example, you could have a dev test cluster. A task definition is the way you model your application. describing how containers will interact together. A task is an instantiation of a task definition. It constitutes a unit of work. You can have a task with just one container, or up to 10 that work together on a single machine. You could have, let's say, Nginx in front of Rails, or Redis behind Rails. And you can run as many tasks on an instance as will fit. Services are instantiated with our second scheduler, create service. A service is made of a certain number of the same task, and these tasks are kept alive. You can specify that a service be fronted by an Amazon Elastic Load Balancer, which makes it easy to balance traffic across containers. But it also gives you a way to discover a service by using a service name and the ELBC name via API calls, for example. I'll talk about this a little more in the future slides. So we have covered the basics. Let's dive into what clusters are and how to make the best use of them. We're going to start with talking about setting up a cluster, and we will also cover IAM integration, monitoring and logging, how to AutoScale, the use of Amazon EC2 Simple Systems Manager, and CloudFormation. So this is the best way to add resources to your ECS cluster. It is by creating AutoScaling groups. This is an opportunity for me to give the following message to operations people in attendance. Think of the resources that your containers will need and choose the instance type that makes sense for your applications. If your containers need more compute optimized performance, then you might want to choose C4 instances. On the other end, if your workload needs a lot of memory, you could use R3 instances, which are memory optimized. You're going to need to create both an AutoScaling group and a launch configuration. The AutoScaling group is a collection of EC2 instances that share similar characteristics and are treated as a logical grouping for the purpose of instance scaling and management. And this is how you scale EC2 horizontally on AWS. The launch configuration is the template that an AutoScaling group uses to launch EC2 instances. We keep ECS optimized AMIs, Amazon Machine Images, up to date. So you don't have to create your own. But feel free to use the distribution you prefer by adding the Docker daemon and the ECS agent. For example, you could use CoreOS. AWS Identity and Access Management enables you to securely control access to AWS services and resources for your users. With EC2 Container Service, there are two IAM policies that we need to define. The first policy establishes permissions for the container instance, or more precisely, the ECS agent that lives on the instance to make calls to ECS API. This is how ECS and the Docker daemon interact through the ECS agent. The other role is for the service scheduler to register container instances with an Elastic Load Balancer on our behalf. And to make this easier, we have made all of these policies, these two policies, available as managed policies in IAM. You don't have to recreate them. Once we have added container instances to a cluster with an auto-scaling group, and we've given the adequate IAM roles, we can monitor our cluster with the following metrics: CPU reservation, memory reservation, CPU utilization, memory utilization. Cluster reservation metrics are measured as the percentage of CPU and memory that is reserved by all Amazon ECS tasks on a cluster when compared to the aggregate CPU and memory that was registered for each active container instance in the cluster. Cluster utilization is measured as the percentage of CPU and memory that is used by all Amazon ECS tasks on a cluster when compared to the aggregate CPU and memory that was registered for each active container instance in the cluster. These metrics are collected once a minute and stored for a period of 2 weeks. Amazon ECS container instances require at least version 1.4.0 of the container agent to enable CloudWatch metrics, but we recommend always using the latest container agent version. These metrics are available on the ECS console as well as CloudWatch. So what is Amazon CloudWatch? Well, it's a monitoring service for AWS cloud resources and the applications that you run on AWS. You see here that we display them as a chart, and you can also define alarms based on their value. You now know that we offer 4 cluster-related metrics. What if you want to add your own set of metrics? Well, you can do so by making use of the Put Metric Data API call or running a script like this one. These scripts are described in the CloudWatch documentation. Amazon CloudWatch associates the data points with the specified metric. If the specified metric does not exist, Amazon CloudWatch will create the metric. When CloudWatch creates a metric, it can take up to 15 minutes for the metric to first appear. The result is that you can add the monitoring metrics that best fit your needs. So we covered the infrastructure-related metrics. What if you want to collect logs from the containers themselves? Application logs. In order to collect and monitor your logs for specific phrases, values, or patterns, we can leverage CloudWatch logs. For example, you could set an alarm on the number of errors that occur in your container's logs, or you could view graphs of web request latencies from within your container. The additional advantage here is that you can look at a single pane of glass for all of your monitoring needs, because such metrics as CPU, disk, I/O, and network for your container instances are already available in CloudWatch. Our approach here, presented on the right, involves setting up a container whose sole purpose is log collecting and log pushing. It runs rsyslog and the CloudWatch logs agent, and we use Docker links to communicate to other containers. You can think of this as a sidecar container. At this point, our cluster is ready to host containers. We have an AutoScaling group, our monitoring is in place. We're looking forward to a successful application. And if the application is very successful, you might meet more demand, and more demand means you might need more resources. Configuring scaling policies is the bridge between the AutoScaling group and monitoring metrics that exist. You can define policies to add container instances or remove them when needed. You can watch your cluster grow in response to criteria that you defined. By the way, when AutoScaling policies to remove one of the instances, aka scaling in as opposed to scaling out, containers on this instance will be terminated. If they are running as part of a service, the service scheduler will create the missing tasks as necessary on instances that have the required resources available. To maintain your cluster, keep it up to date, you can easily do so using Amazon EC2 Simple Systems Manager. SSM enables you to remotely manage the configuration of your Amazon EC2 instance. So you can run commands on all your container instances with one simple operation. One use case for this could be to install or update services that run at the host level. All you need is to have that SSM agent installed and the appropriate policy attached to the instance with an EC2 role. All of the elements we described so far, like AutoScaling groups, IAM roles, and policies, do not have to be created manually. As a matter of fact, we recommend that you define them once with CloudFormation. AWS CloudFormation gives developers and system administrators an easy way to create and manage a collection of related AWS resources, provisioning and updating them in an orderly and predictable fashion. You don't need to figure out the order for provisioning AWS services or the subtleties of making those dependencies work. CloudFormation takes care of this for you. It's available at no additional charge, and you pay only for the AWS resources needed to run your application. Here is what CloudFormation looks like. This is one template that could include ECS references. So it describes all the resources that you need in a JSON formatted document that can be easily shared and versioned. This makes for reproducible and traceable infrastructure as code. So here on the slide you see that we define a cluster in the first few lines. Then we create an AutoScaling group, which is going to launch container instances according to an explicit launch config. We have called this launch config container instances. Going into the second part of the CloudFormation template here, this part describes the launch configuration. In CloudFormation, you can use the commands key to execute commands on the EC2 instance. The commands are processed in alphabetical order by name, hence why we are calling this the first one 01 add instance to cluster. With this feature, you can see here in the middle that we can specify which cluster the EC2 instances should join. And this is done by adding an ECS underscore cluster equals and then the name of the cluster line to /etc/ECS/ECS.config. If no such parameter is defined, the container instance will join your default cluster. I should say that you can now visualize your CloudFormation templates as diagrams, and you can edit them using a drag and drop interface with the AWS CloudFormation Designer. Right, this covers our resource part. You now know how to create a dynamically scalable cluster on ECS, complete with logging, monitoring, and remote command execution. Let us take a look at how to most efficiently run containerized applications on this resource pool. We are going to talk about task definitions as well as the EC2 container registry. Task definition is a way we model our applications to run on ECS. So what are tasks and how should we plan them? Well, if my application is made of multiple components, I have two choices. The components can either sit within the same task definition if they are part of the same function, or you can separate them into different task definitions if the components need to be independent from one another. Often people wonder about cross-host links. Well, those don't go in your tasks. Put them behind an ELB or a discovery system and make multiple tasks. We'll talk about this a little more. You can define multiple containers and data volumes in a task definition. A task definition also lets you specify Docker concepts like links to establish network channels between the containers and the volumes your containers need to, or volume mappings. This is all done in a JSON formatted file. If you have used Fig in the past or Docker Compose recently, you should be familiar with the shape of a task definition. Task definitions are tracked by name and revision, just like source code. So this is a WordPress example of a task definition. Note that you can easily generate an empty task definition template with the -- generate CLI skeleton AWS CLI command parameter. And you can find out more about this in our documentation. This task definition specifies WordPress on PHP in a container and MySQL in another container. You can see on the 5th and 6th lines that we create a link to MySQL. Using the WordPress Docker image, in this case, will be sourced from the Docker Hub. And by default, we use Docker Hub. But you can specify your own EC2 hosted trusted registry or use the Amazon EC2 container registry. Notice how we provide resource requirements here. I'm going to go a little deeper on these resource requirements. The memory parameter needs a non-zero integer. The Docker daemon reserves a minimum of 4 megabytes of memory for a container, so you should not specify fewer than 4 megabytes of memory for your containers. This parameter maps to memory in the Docker Remote API and the -- memory option when using Docker Run. You can consider memory a hard ceiling. If your process ends up using more than the required amount, in this case 500 megabytes, it will be killed. CPU, on the other hand, is like a floor. Your process can use all available CPU unless it is used by other containers. A container instance has 1,024 CPU units for every CPU core. This parameter specifies the minimum amount of CPU to reserve for a container, and containers share unallocated CPU units with other containers on the instance with the same ratio as their allocated amount. And by the way, this parameter is optional, the CPU one, and it maps to CPU shares in the Docker Remote API and -- CPU shares option when using Docker Run. So that's the second and last part of our task definition. You can see here that we are providing password as an environment variable. This is not recommended for production, as these environment variables will be available via the docker inspect command. You might want to use a tool like HashiCorp Vault or Kiwiz, a system for managing and distributing secrets, which was open sourced by Square. You can notice at the bottom, close to the bottom, the essential flag. This flag applies at the container level. If the container goes down, the whole task will be terminated. And finally, you specify family, which will give a name to your task definition. Further changes to this task definition will increment the revision number. Once your task definition is created, scheduling it onto a container instance with available resources creates a task. As I mentioned, before you can pull images from the Docker Hub, you can also use Amazon EC2 Container Registry to host your own container images. Amazon ECR is a fully managed Docker container registry that makes it easy for developers to store, manage, and deploy Docker container images. First thing you will need is to set up a repository. And you can use the namespaces and let different teams use different images that have the same name. In order to set up ECR, the first command you will run is ECR get login. What it does is it returns the Docker login command that you need to run to authenticate with Amazon ECR. Then you can create your repositories using the next AWS CLI command, AWS ECR create repository. You can then build a new image or tag an existing one, and you're ready to push to ECR. Linking back to our initial slide about defining policies, you should note that the user creating a repository will have full access, and you can use IAM policies or repository policies to allow access to other parties. These are policies that we can use to allow access to our users. The first one, Amazon EC2 Container Registry Full Access, allows full administrators access to Amazon ECR. The next one allows power user access to Amazon ECR, which allows read and write access to repositories, but it does not allow users to delete repositories or change the policy documents applied to them. And then the last policy is self-explanatory. It allows read-only access to Amazon ECR, such as the ability to list repositories and the images within, and also to pull images from Amazon ECR with the Docker CLI. So we covered cluster concepts, tasks, and repository. Let us dive deeper into services. In this section, we will discuss monitoring and logging, how to scale services, mechanisms for service discovery and deployment. Starting with monitoring, there are 4 metrics available, again, for each of the services that you create on ECS. And they are CPU reservation, memory reservation, CPU utilization, memory utilization. Service utilization is measured as the percentage of CPU and memory that is used by the Amazon ECS tasks that belong to a service on a cluster when compared to the CPU and memory that is defined in a service's task definition. Each minute, the Amazon ECS container agent on each container instances calculates the number of CPU units and megabytes of memory that are currently being used for each task owned by the service that is running on that container instance. And this information is reported back to Amazon ECS. For example, let's say a task definition for a service reserves a total of 512 CPU units and 1,024 megabytes of memory for all of its containers. The service has a desired count of 1 running task, and it is running on a cluster with one C4.large container instance. C4.large has 2,048 CPU units and 3,768 megabytes of memory. And for the purpose of this example, let's say there are no other tasks running on the cluster. Well, if this task is performing CPU-intensive work during a period and using all 2,048 of the available CPU units and 512 megabytes of memory, then the service will report 400% of CPU utilization and 50% of memory utilization. All 4 metrics are sent to CloudWatch every minute, and they're kept for 2 weeks so that you can access historical information and gain a better perspective on how your services are performing. And of course, you can see these metrics both on the ECS console and the Amazon CloudWatch console. At reInvent, the Amazon Web Services annual user conference, we extended the task definition to include most of the Docker options. Among these are the ability to specify the logging drivers for your containers. At the moment, the list of available log drivers includes JSON file, syslog, journald, gelf, and fluentd. You will need version 1.18 of the Docker Remote API, which means that you will need Docker 1.8, I think. Now, what you would get from typing docker log in your command line is available through these engines. So for example, if you want to collect your logs in Logstash, you would use gelf or jelf, which is probably the same kind of debate as GIF and GIF, so I'm not going to get into this, but for Fluent, you could use fluentd, for example. Scaling services can be done automatically as well. In this example, that AWS partner class method put together, a combination of CloudWatch, SNS, and Lambda is used. Right, so I need to give you a quick introduction about both these services. Amazon's Simple Notification Service is a fast, flexible, fully managed pub/sub messaging service. And AWS Lambda lets you run code without provisioning or managing servers. This automatic scaling works by first defining an alarm on one of the metrics in CloudWatch. In this example, it could be a certain amount of requests per second received by an Elastic Load Balancer. The alarm will trigger a message to be sent on an SNS topic. Upon reception of the message, a Lambda function is triggered. This function will increase the number of desired tasks for a service up to a predetermined limit. You could also create a scaled-down automation with the same components. One common scenario of use for ECS is to deploy microservices applications effectively. When deploying microservices at scale, it is often crucial to offer a mechanism for service discovery. One way of providing service discovery on ECS is to use Route 53 and ECS Services. You can create a Route 53 private zone for your ECS cluster. Then you would define ECS services for each microservice or component of your application. We associate a DNS CNAME to our ELBs for each service. Optionally, on the container instances for the ECS cluster, you can use DHCP option sets to set the search path on host to a .domain name, such as, let's say, .mydomain. So the services need only know the name of the service that they want to talk to. And by the way, this solution is what was implemented in the Empire setup by Remind, and we will talk about it more in the coming slides. As we've seen, creating a service will maintain application availability, and it allows you to scale your containers up or down to meet your application's capacity requirements. Amazon ECS needs permission to register and deregister container instances, to register and deregister them with the load balancer when the tasks are created and stopped. This will be done through an IAM policy and a role at the time of service creation. Note that if a task fails the ELB health check, the task will be killed and restarted. One way of deploying services is by updating the service with a new revision of the task definition. This will basically roll out the new version in your cluster. And there are two additional configuration options for deployments. The first one is minimum healthy %, which is the minimum number of healthy tasks that you want to have running during an update. And then the second one is maximum %, which is the maximum number of tasks you want to have running at any time during the deployment. So let us see how this plays out graphically. There you go. On this example, we have a cluster with 5 container instances, and we want to deploy using the least space in our cluster. So you can set the minimum healthy % to a half, so at least 50% of our tasks will be healthy at any given time. And then maximum being 100%, so that no more than 4 tasks will be running at any time. The new version gets rolled out to 2 tasks, keeping the other 2 untouched. And once the update is successful, the deployment can move to the next. This is probably a good time to mention that when the service scheduler replaces a task during an update, if a load balancer is used by the service first removes the task from the load balancer and waits for the connection to drain. Here's another deployment tactic. It's less resource constrained, and this method will deploy as quickly as possible. You can set the minimum to 100%, maximum to 200%. And we keep our existing containers running. You add an additional 4 tasks, deploy in a block to 4 new instances, and once the new version has been deployed, then the old tasks are stopped. A quick point here. Tasks for services that do not use a load balancer are considered healthy if they are in the running state. Tasks for services that do use a load balancer are considered healthy if they are in the running state, and the container instance it is hosted on is reported as healthy by the load balancer. Here's another method for deployment. Blue-green is part of continuous deployment, and it is a release technique which reduces downtime and risk by running 2 identical production environments. It's usually automated, as the switch needs to happen quickly. The method we showcase here will feature 2 services, each fronted by an ELB, and it also features the weighted round-robin feature from Amazon Route 53. And if you're not familiar with Route 53, it is a highly available and scalable cloud DNS web service. So at first, all requests go to the blue service as per Route 53's record. And then you can set up a new version of your service and have it run in the same cluster. When the green service is up and running, you can switch the weight to go 100% to green instead. Thanks to ECS extensibility, it is possible to plug in your favorite continuous integration, continuous deployment solution. In this example, a commit to GitHub could update a webhook and trigger a job execution. Jenkins could be used to compile and assemble the application with all the dependencies. The Docker build and publish plugin in Jenkins would build the Docker image, and then a call to the Amazon ECS API will update the service to use this new image. So you can go from developing on your laptop to an application running at scale on AWS with a simple commit. Now, Jenkins is just an example. Our partners have created CI/CD solutions with Amazon ECS. Worker has a tutorial on deploying a 3-tiered microservice application consisting of a simple front end, an API, and a Redis backend. CodeShip leverages their own CodeShip/AWS-deployment, that's the name of the container, which lets you plug in your deployment tools without the need to include them in the testing or even production container. Shippable offers a pipeline which utilizes Shippable CI to initiate the build of your application, synchronization of your code from source control, and execute unit tests and create tag push a Docker image to ECR. Then it uses shippable formations to trigger deployment onto ECS and execute functional integration and smoke tests. Soleno Labs has a blog post out explaining how to configure Soleno CI to trigger a build on commit and deploy to both Amazon ECR and ECS using passing builds. Upon passing builds, sorry, my bad. And you can see that integration is available for both ECS and ECR. So we have now covered clusters, tasks, and services. Now let's take a look at a number of solutions that can help you deploy your applications to ECS without worrying about the underlying infrastructure. Here are 3 solutions that leverage ECS and aim at running containerized applications easily. And let's start with AWS Elastic Beanstalk. Elastic Beanstalk is an easy-to-use service for deploying and scaling web applications and services developed with Java, .NET, PHP, Node.js, Python, Ruby, Go, and Docker on familiar servers such as Apache, Nginx, Passenger, and IIS. When using multi-container environment on Elastic Beanstalk, your containers are actually deployed on ECS. In this situation, Beanstalk will create all the resources for you: cluster, task definition, ELB, and so on. And this is the way that Elastic Beanstalk defines the containers. It uses a JSON file, dockerrun.aws.json, that is similar to a task definition. One neat feature is that Elastic Beanstalk configures additional volumes for logs, one for each container, and these should be mounted by your containers in order to write logs to the host instance. Beanstalk is a great way to get started with multi-container applications. It does a lot of the heavy lifting for you, so you can focus on your product. It's particularly well suited for 3-tier web applications. And if you outgrow Elastic Beanstalk or feel the need for more control over the scheduling of your applications, you can easily turn an Elastic Beanstalk setup into an ECS one. The second solution is Convox, a private platform as a service solution built on top of ECS. This solution uses the concept of a rack. A Convox rack gives you a place to deploy your web applications and mobile backends without having to worry about managing servers, writing complex deployment recipes, or monitoring process uptime. The rack installer provisions all of the AWS components necessary to create a robust, developer-friendly platform. In the background, Convox leverages such AWS services as CloudFormation, ECS, and ELB. Once the AWS services are provisioned, the final components of the rack are installed. And these include the rack API, a private Docker registry, and the custom Convox agent for ECS. Now, a point to note is, as of January 2016, racks running in the US East region use Amazon ECR to store images. So Convox uses 3 files to build and run your development environment: a Docker compose.yaml file, or a proc file, referred to as the manifest of your application, and then two optional files. The first one is Docker file to document your build, and the second one is .env, a file to contain development secrets. The Docker file and .env files they're there to support information that is referenced in the manifest and required for a deterministic and declarative way to run your software. This allows the manifest to act as a single source of truth. The build instructions in the Docker file define how to create your software from source code. And you can see the few steps that are needed here to deploy an application. At the very bottom, at the very end, the output of convox deploy is any endpoint that your application would make available. The last solution I wanted to mention today was the Empire project by Remind. Remind, as a company, offers a communication tool that helps teachers connect with students and parents. And they recently open sourced this project, which they describe as a Heroku-like platform as a service. And the way it works is that upon deployment, a proc file will be extracted, and this proc file will map directly to an ECS service. Empire's routing layer is backed by internal ELBs. Any application that specifies a web process will get an internal ELB attached to its associated ECS service. When a new version of the app is deployed, ECS manages spinning up the new versions of the process, waiting for old connections to drain, and then killing the old release. When a new internal ELB is created, an associated CNAME record will be created in Route 53 under the internal top-level domain, which means you can use DNS for service discovery. If we deploy an application named feed, then it will be available at http://feed within the ECS cluster. Applications default to only being exposed internally unless you add a custom domain to them. Adding a custom domain will create a new external ELB for the ECS service. And this brings us to the conclusion of this presentation. I would like to now open the floor for some of the questions that you may have asked or you would ask now. Also, I should mention that these slides will be available on SlideShare in a few days.